Okay guys, in this video we're going to be exploring the concept of what we call a geometric probability, which is a form of theoretical probability, but as you might guess, it gets its name from the fact that we're going to be using shapes involved here. So looking at this, it says we can use the area to find the theoretical probabilities at times if all outcomes are equally likely and events occur randomly. So consider the following thought experiment. I have here a dartboard, and so let's assume we throw a dart at this board here. It says that our dart is equally likely to hit any point inside the square board. So when this happens, and we have a geometric shape here, we say that this is a theoretical probability because anything is just as likely to happen as anything else. This dart could really land anywhere on this board. And so since it happens randomly and everything's equally likely, then we're going to interpret this as a geometric probability, or a special type of theoretical probability that we call a geometric probability. So the question we're about to answer here in a moment is, are we more likely to get 10 points or 0 points? And when it comes down to it, when you look at this situation here, it's kind of like asking this question, well, which takes up more space on the board? Because the bigger the space it takes up, well, then the more likely I am to just randomly hit that spot. So really, when we look at this, we are going to be concerned with finding the areas here. So let's go ahead and we'll type in a little ditty here that we can put into our notes here. This will show up. Here we go. There we go. To find a geometric probability of an event, we will take the area of a favorable location divided by the area of the entire space. So with respect to how this is related to our theoretical probabilities say take the likelihood of some event would be the favorable outcomes divided by the total number of outcomes. When we look at this situation here, we say that the probability of an event will take the area of a favorable location. This right here is going to be our event space. Okay. And this right here, the area of the entire space, that'll be what we usually refer to as the sample space. So in a theoretical game or probability, we say the set of all possible outcomes is our sample space. Well, the set of all possible area here is going to be our sample space. So when it comes to the probability of an event, we're going to write this down here. We're going to say the area of the favorable region divided by the area total region. Okay. All right, so some things really quickly here. What I'd like to do before we go ahead and assess a situation is write down some of our more common area formulas. And so our area formulas here, there are 4 at least initially that I want to make sure that we're all very comfortable with. But these would be for a circle, okay, as we see here, a square, followed by a rectangle, which is a little bit different than a square, right? A square has all 4 sides the same length. And then our triangle here. These shapes are going to come in handy, especially since we can really partition a lot of other shapes into these here, make them into sub-shapes that are circles, squares, rectangles, and especially triangles. So when it comes to a circle, we're going to say that our pi times our radius squared is our area. And a good way to remember this is because our radius is squared, it kind of implies that it's 2-dimensional here. So we're finding a 2-dimensional area. A square, you're going to see me write this s squared, where s equals the side length. So just take one of our sides and square it. And really this happens because when we think about a rectangle in general, it's base times height. Well, if you have side times itself, it becomes side squared. And then our triangle here is very similar to our rectangle. It's going to be 1/2 base times height. So keeping these in our back pockets here, let's go ahead then and try to find out how likely we are to get, say, 10 points or 0 points. So the question of the day is, are we more likely to get 10 points or 0 points? Let's go ahead and take a look at this space here. So we're going to start with finding the probability of 0 points. So you'll notice that the very first thing I do is I write this symbolically. In our function notation, we say, what's the likelihood that this event occurs here? So there are some things that I'm going to need to know, specifically the area of the total region, and then the area of just the 0 point region right here. So when we look at the area of the total region, the very first thing I want you to consider is that each of these, according to this problem here, is 3 inches. And so that would mean that the total distance across this here, at least the radius length on a circle would be 9, and the total distance across the square would be 18, and I'm going to write inches here. So our square is 18 inches by 18 inches. We're going to say the area of the total square here, area total, would be equal to 18 times 18, or in other words, 18 squared, which is 324. So this is going to serve as our sample space here. The question is, how much area does the 0 point region take up? So we're going to kind of analyze this here, and the thing that makes it a little bit difficult is that these 0 point regions aren't really any of these shapes that we've listed here. So what we're going to have to use is this idea that if I take the area of the total space here, which is this 324, and I subtract off the area of, say, this larger circle here, it would just leave behind these 4 areas here. So the way I would craft this is, we're going to take the area of the total space, which is our square area, 18 squared, and we're going to subtract off the area of the large circle, which has a radius of 9 inches. So we're going to say minus pi times 9 squared. This right here on the top represents the areas of the 0 point region together. And this is all over the area of the total amount, which is 18 squared here, or the area of our square. So simplifying this a little bit, on top we get 324 minus 9 times 9 is 81, and we have pi. And this is all in parentheses here, and this is all over 324. So really, to find our probability here, we just now need to put this into our calculator. So let's go ahead and get our calculator on, and we are going to craft this just like you see it here with the parentheses and everything. Let's put in 324 minus 81, and our pi key is behind our caret key here. So in parenthesis, we're going to divide this by 324. And what we get is this number right here, 0.2146. So let's go ahead and record this. We would say that this, is approximately 0.2146, which is our decimal probability. And we could even call this, if we scooch the decimal twice to the right, about a 21.46 chance of hitting the 0 point region. Now the question is that more or less than the 10 point region? Well, let's go ahead and analyze this event then, the likelihood of this event occurring. So in this case, it's still going to be out of the total space here, out of the area of the square, but the question is, well, what's the area of the 10 point space? And we notice that this is a circle, and the radius of this circle is 3. So in this case here, no subtraction needed. We can just say the area of the 10 point space is pi times 3 squared, which as we simplify this becomes 9 pi over 324. Now I will tell you that this reduces, but ultimately I'm after the decimal. So instead of trying to reduce this here, we'll go ahead and say that this is our exact value in a non-simplified state, and we'll just type it in here. We have 9 times pi divided by 324. We don't need the parentheses on the top this time because we weren't subtracting or adding anything. We get 0.0873, so approximately 0.0873, which is, it's about a 8.73% chance. So to make a conclusion here, or draw a conclusion here, it might be something that doesn't shock you at all. The 0 point region definitely takes up more space than the 10 point region. Maybe not so obviously, but it becomes clear when we look at the probabilities here. We got a 21 and almost a 0.5% chance of hitting the 0 point versus the almost 9% chance of hitting the 10 point region. So what I'd like to do is kind of try this again with a couple other examples here. With this number 8, and we're going to use the same diagram here. But looking at number 8 here, it says in example 4, are you more likely to get 10 points or 5 points? Let's look at our 10 point region versus our 5 point region here. And so in this particular instance, we'll go ahead and go with our probability of 10 points. Thing is, we just kind of evaluated this here, but I do want to reconstruct this. It would be out of the total area here, we need the area of the 10 point region, which is a circle of radius 3. So here's our 9 pi out of 324, which we discovered was about an 8.73% chance of occurring. The question now is, are we more likely to get 10 points or 5 points? Well, just using my common sense here, I think that 5 probably takes up a little bit more area than the 10. But let's go ahead and take a look at this algebraically here. So 5 points, are we more likely to get it? Now the thing is, it's still out of the total sample space, which is this area of our square that is 18 by 18 on its side. So out of 324, the difference here is, how do I find the area of just the 5 point region? And the hard part there is, we know that it's a circle and that the radius here of our 5-point region is 3 plus 3 is 6. But if we do pi times 6 squared, you're going to be finding the area of the 5-point region and the 10-point region. So the way we're going to have to compose this is, let's find the area of the 5 and 10-point region by finding the area of this 5-point circle here. And then what we're going to do is we're going to subtract off the area of the 10-point region, which would leave behind everything out here. This is something pretty common. We have to compose these spaces here. So the area of our 5-point region would be a circle of radius 6, so pi 6 squared, minus our circle in the middle there, radius 3, pi 3 squared. And so what we get is 36 pi minus 9 pi. In other words, 36 minus 9 would be 27 pi over 324. So already we can tell that this is bigger than 9 pi over 324, but let's go ahead and get a value here. We want to know, what is this as a decimal? So 27 pi divided by 324, we would get 0.2618-ish. So let me scroll over here. 0.2618-ish, which is about a 26.18% chance. So to draw a conclusion here, what are we more likely to hit, the 10 or the 5-point region? We're more likely to hit the 5-point region than we are the 10-point region. Okay. So for this last geometric probability here, maybe I'd like you to try this first before I develop the solution with you here. So pause the video, but then continue to see what we get here. After you hit pause though, let's go ahead and write this symbolically. It says, are we more likely to score points, so 10, 5, or 2, or just to get none? So what I want to do is I'm going to start with the 0-point region, just because we had already kind of explored this previously. We say out of this entire space, which has an area of 18 by 18, what's the 0-point region? Well, it would be the entire space, 18 by 18, so 18 squared, minus the area of our large circular region here, which has a radius of 9 inches. So minus pi times 9 squared. This would give us our 324 minus 81 pi all over 324. Now, because we have already previously found this, our 0-point region, let me scroll back up here, was this 0.2146. I'm going to borrow just to save us some time here. You should have gotten the same thing, 0.2146. And this time I'll leave this as a decimal. Now the question is, are we more likely to get points? So we say 2 or 10 or 5 or 10 points. It could be any of these. So this entire space here would just be this circle of radius 9. In this case then we could say out of our entire area of our entire region here, we could say what's the area of the larger circular region, which is a circle of radius 9, so pi 9 squared. So we would get 81 pi over 324. And looking at this as a decimal, let's go ahead and take a look. We have 81 pi divided by 324. We get down to 0.7854, so about 0.7854, which is this guy right here. Now, this means that we're more likely to get this 2 or 5 or 10-point region space, and we can see it clearly with our decimals here. So when it comes to finding geometric probabilities, they really are just theoretical probabilities. We assume that any space is equally likely to be hit, and if that's the case, then we want to know how likely is it we hit an individual space. We'll just find the area of that favorable space divided by the total area, or our event space over our sample space there. Cheers.